All right, guys. Sorry this video is coming out late. It's been a busy week. Um, but we should be able to knock this out pretty quickly. Adding and subtracting polynomials is going to be very similar to how you added and subtracted different variables. So we still do the like terms and everything, except now we're dealing with exponents. Also, we're going to keep in mind that if we're subtracting, we have to account for the distributive property when we're just subtracting something. So honestly, this one shouldn't be too bad. We should be able to get through it fairly quickly. So let's take a dive in. Adding and subtracting polynomials. So in this lesson, we will determine the differences, sums and differences. So sums being adding, differences is subtracting polynomials. Um, looks like they needed more space down here. So we're going to look for the structure. We're going to understand um, the system of how we're going to do it with integers, um, closed operations. Closed operations, I feel it's too complicated of a word, but in number theory, it's this idea that if you're doing that operation, you don't get something else. Like we're not going to add some type of polynomial to another polynomial, and then all of a sudden it's like, oh wow, all of a sudden it became an exponential function. Um, it's not going to become an exponential. It's still going to be some other type of polynomial. So that's what it means by closed under an operation. It's not going to turn into an exponential. It's not going to turn into a radical function. We learned in the other one that even though radical functions can kind of be polynomials, they are a little different. So they don't change that drastically. All right. So let's answer some questions here. So if we're adding these polynomials, first things first, we're going to want to distribute. So I'm going to get negative 2x plus 4 because that's already there, plus 4x plus 2. So right off the bat, I see that I have some like terms here. I have this 4, and then I also have these right here. So if I combine those two together, I'm going to do the lime green one first. I get 2x plus 6. So looking at that, I'm going to go over here and I'm like, okay, 2x plus 6. Boom, right there. Now, remember I mentioned we're going to have to do the distributive property here. So this negative comes along with the 4 when we distribute. So let's distribute here. Oops, let me grab my pen. Distributing to here, the whole negative 4 comes here. So we end up getting 6x plus 10 minus 4x plus 4. Now that's an important part. A lot of people think that this 4 only touches the first number. We're distributing it to all of it. And a negative are going to make that positive. So now that I have that done, I'm going to get my x's together, 10x, and then 10 plus 4 is 14. So I should have 10x plus 14. I already see it. It's right here. Bring it down. Let me erase the board. And again, guys, I'm sorry if I'm going fast, but feel free to rewind if you have to. So again, we're going to distribute. This one, I'm only distributing one number. The other ones, it's a plus. Technically, you do distribute a plus, but it's not going to change anything. If you multiply by a positive number, it stays positive. If it's a negative number you're multiplying by a positive, it stays positive. That's one thing I think people don't really cover when they do this is think about it. This plus left this the same. This negative changed it. This negative changed it. So negative numbers cause the change. It's not a matter of the same numbers are always positive and different numbers are negative. It's that negative changes things. So looking at this, we're going to get 2x minus 14 plus 8x plus 20. So I'm going to circle my constants. That's going to be 6. My variables going to be 10x. So I get 10x plus 6. And that should be my last one here. Oh, what happened here? Negative 4, 10. I see what happened. It was a stupid mistake. I got 6 and 5. 6x plus 10. So the 14 was right. My issue was this negative. So that's 2x. So it's 2x plus 14. That was a stupid mistake on my part. Let me fix everything else. So careful with that. That was really dumb on my part. This one was 2x plus 6. All right. I ignored this negative, and that really messed me up. And then here you can see the work. They're distributing it, and they can do it. And then here's where I messed up. Here's the positive 6 and the negative 4, and I treated it like a positive 4. All right, moving on. As always, the intro videos are really helpful. I honestly, like when I see this, I'm like, this doesn't feel like the Edmentum I come to see by their problems. So if you're ever having trouble with the problems, make sure you did watch any of the videos. They do a pretty good job of explaining it. All right, so moving on. An introduction of polynomials. So we're going to talk about what polynomials are. So adding and subtracting polynomials. So polynomials can come in all kinds of forms. We can keep adding to. So a constant, even though there is no variable, a constant is still a polynomial. A linear function is a polynomial. It has a variable. There's no x's in the exponent. You can have exponents in the polynomial. For example, quadratic is a really good equation. We've dealt with them for parabolas and stuff. It has a 2 in it, but the x is the base. So whenever you're dealing with your variable, your input has to be the base. And it comes with all kinds of other polynomials. So there's usually this idea of a coefficient. We've talked about these before. Coefficients are the numbers in front of the variable. There's a variable itself and a constant. Constant, think about what's the opposite of a variable? A constant. A variable means it changes. So this changes depending on the input. So whatever x value you're talking about, it will change. Constant to 7 isn't going to change. Coefficients, they stay the same for the formula, but think about it. Yes, it stays the same, but you're eventually going to multiply it by this variable. So coefficient is something that gets multiplied by the variable later on. So quadratics, all of these, we're going to think about the highest power. So if we're thinking about the powers of polynomials, a constant has no power, no exponent. So its degree is 0. A constant has a degree of 0. A linear function has a degree of 1. Its power is 1. The highest power of a quadratic is a square. So this is how we identify it. You can have a quadratic that doesn't have an x. It doesn't have a constant. So they're identified by their highest power. You can't call this function a quadratic when it doesn't have an x squared. Doesn't work that way. All right, so here the degrees, like I mentioned before, the degree is the highest power in a polynomial. All right, so let's get to this. So we're going to look at the highest degree. So it's an x, so the highest degree is a 1. I'm looking at this, the highest power is a squared, so the degree is 2. Looking at this one, highest power is 2, so the degree is 2. This is a constant. It doesn't have a variable, so its degree is 0. This is a linear function, so its degree is 1. And the only reason why it's linear is in that form, y equals mx plus b, or better yet, you can just say it's linear because it doesn't have any exponent. This is linear as well, and this is a constant. So there we go. Pretty self-explanatory how to do those. It's also an easy way to know if something's linear or not. Like, for example, when we were dealing with linear functions back last semester, there was linear functions that looked a little like this. Whereas there's also linear functions that look like this. Now, the way I knew you can tell that these are linear is there's no power on the x, or y for that matter. But usually when we talk about a function, it's like y equals something. All right. So whenever we're writing something in standard form, we always want the highest power on the left. And then we're going to decrease the power on the right. So this is how you would write it. This n just represents the highest power. N minus 1, that just means one less, one power less. So if this is like a 5, this would be a 4, this would be a 3. This could have been a 7, this could be a 6, so on and so forth. Until eventually we get to the squared, and then the no power, and then this. So these little terms right here, they're on the bottom, they're called subscripts. So this is subscript 0. I always call it not. So this is a not, meaning that it's the very first one. And this one would be a sub 1. So it goes in order from your constant going up. The reason for this is you can count this increasing this way. You have no idea when you're going to stop with n. That's why usually the last terms are called n, and n minus 1 being the term before the last one. These you're like, okay, cool, this is 0. uh, I have to have a constant. You have to have a constant, so you have to have a 0 at least. You don't have to have an x. You don't have to have a squared. You don't even have to have any of this stuff. Probably going on a little too long with that, but a lot of people get confused with the notation here. All right, so we can talk about this. So this is the notation for a standard polynomial. And then here they're talking about how the degree decreases until eventually we get to nothing. These also decrease until we get to the actual constant, the a naught. Before that, there's the a sub 1 times x. A minus 1 is coefficient before that, and then they talk about, so this is everything I literally just explained right now. X is always a variable. There should be one for each term. This one, in this case, there's nothing because it's x to the 0. These are the highest power and the second highest power. And then these little the terms called ellipses, the series of dots. It's called an ellipses. This just means it's continuing because we have no idea how many terms are between here and here. Technically, these might not even exist. So it's just saying, like, this is how you write it. It could go on until you get to here. So remember, this would be if it's a quadratic because it's squared, linear if it doesn't have a power and it's just an x, or constant if it never changes. And constants are I think one of the biggest ones they use is always the phone bill one. Like if you get a plan, your phone bill is usually so much, but then there's a variable cost where, like, if you use too much data or something, it increases based on the number that you're multiplying by. So if you use a lot of data, there's a number you multiply times what you went over. All right, so let's talk about these. Which one of these are polynomials expression in standard form? So this has the highest power in the front, so this one's good. This one's, we're going to talk about this later on. This is known as factored form. It's not standard form, although you can look at this term right here and like, oh, this is a linear function in standard form. This is a linear function in standard form. Because you're multiplying, it's not considered standard form. This later on we'll find out is actually a quadratic in disguise. This is standard form, highest power on the left. This is standard form because it's just a constant. This is not standard form because these x's will end up being 10x squared. So it's not written in standard form. So there you go for those. Let's talk about monomials and binomials and trinomials. So these are terms when we're talking about. Oh, that was portrait. Ah, that was a poor choice of words. Um, this is vocabulary to talk about what's known as a term. So, for example, 3x is a term. 4 is a different term. So you put these together, they're two different terms. So they're separated by a plus or a minus. They kind of fall within themselves. Like I could say, this is a quadratic, and it's a term all by itself. It's a monomial quadratic. But if I add, let's say I have 3x. 3x is a linear monomial. But if I add these two together, it's a quadratic. It's just a binomial quadratic. The fact that this is a linear doesn't affect it. So adding on different terms will not change it because the degree doesn't change. It's just going to change how the graph looks. And you know what? Let me do a little example so you guys can see what I mean by that. So let's say I have this 3x squared. And these are going to have nothing to do with each other when I do them separately, by the way. And I have 3x. So I have this line. So now I'm going to hide these for now. You're going to see that they have nothing to do with each other. It's just a completely unrelated quadratic. Well, I guess unrelated is poor choice of words. You can see that the shape is pretty similar. Actually, no, this one looks a little bigger. So main idea is that adding them together has nothing to do with it. The only thing you really care about is what the power is. It's just a different quadratic. It just has different terms that creates a brand new polynomial. So when we're looking at this, we can classify polynomials by their degree, and we can also classify them by the number of terms. So like I was mentioning before, I had a quadratic binomial. So something like this as a constant instead of a linear function, but this is a quadratic binomial. This is a quadratic trinomial. Again, these do affect the parabola, but not in the sense of like, oh, this is a parabola with a line on it. It affects them all very differently. And there's all different types of math to study how they get changed. Describe each polynomial expression by type and components based on the examples shown. Okay, so the first one, is a quadratic, quadratic, because of the squared binomial. Uh, all right, first. Second is a quadratic as well. Quadratic. Um, there's three terms. 1, 2, 3. They're being separated by these plus or minuses. Quadratic trinomial. The last is a linear because it has power to the 1. Linear monomial. All right, so we get those down. All right, so let's talk about sum and differences. So sum and differences, as we saw, adding and subtracting doesn't really change polynomials too much. We've already had some practice with them, but not too much to talk about what we're going to be doing on this. Now we're going to start describing what happens when we add and subtract these polynomials. We're not going to get too much into shapes because, like I mentioned, if you add a linear function to a quadratic function, what comes out doesn't really look the same, except for the quadratic is going to look more like it because it's the same type of function. So let's take a look at this. So by operation, they just mean mathematical operation. They have a little picture of a doctor here to make it cute. Um, so if I kind of talked about this earlier, if you add or subtract a polynomial, you're gonna get another polynomial. If you have two polynomials being added together, you get a polynomial. That's what it means by being closed under that operation. It's not like, oh, I'm gonna add a polynomial and another polynomial and get that square root that I was talking about before. It doesn't happen. So let's say I added these two polynomials together. I would do all the like terms, so I would rearrange it so all the like terms are together. They put parentheses. I like circling them because I don't like rewriting my functions this many times. And I'm going to add them inside. So these add up to 12, these add up to 8, and I still get a polynomial, a simplified polynomial, nice and simple. So with negative signs, you have to remember to distribute. A lot of people, what they do is they just remove the parentheses. Don't do that. You can see here what happens. So this guy's reminding you, distribute that negative sign. So you want to definitely distribute the negative sign. All right. So let's take a look, and so Grace are simplifying the polynomial. Which statement is correct and why? So let's take a look at all of them together and see if we can figure out where they made a mistake. So if you look at this, we're going to distribute this 6. Okay, that's right. We distribute the negative here. We get negative 12, positive 6. Okay, Grace is looking good so far. Then the negative 3x and the negative 12x, they're putting them together. We have 6 and 16. So Grace's looks correct. Let's take a look at Chelsea. Chelsea, she distributes it. Chelsea did not distribute the negative to the 8. So Chelsea is wrong because she did not distribute the negative to the 8. And this is kind of like the mindset of a math teacher when we ask you to show your work. Obviously, if we look at these answers are wrong, but what I can do here is if I was grading this, I would be like, okay, so Chelsea's distributed that fine. That's great, but she forgot to distribute the negative. So I would mark points off for not distributing the negative. Whereas if Chelsea just went, here's my answer, well, you get all of it wrong. You don't get any partial credit. This one, so um, and because he did not distribute the negative at all. All right, so Chelsea ends up being correct because she distributed the negative to the 6 and to the 8. If we look here, she added correctly. Grace is the only one. Grace is the only one to have distributed correctly. Distributed and added correctly. And I use the word added as kind of like a universal term for subtraction and addition. You're finding some and that just because addition is just adding or subtraction is just adding negative numbers. So here you can see that Grace got it right, and you can see the other ones made a mistake in distributing the negative signs. They did it a lot easier than I explained it. All right, so let's think back on addition and subtraction. You did with linear expressions. What kind of expression did you get as a result? Now imagine. So this is just more examples of distributing and adding these. But what are we going to do if we do these? Well, we've already done linear. So this is pretty much the same thing. You're just going to distribute and add. So again, watch these videos. They are surprisingly helpful. I am surprised at how much detail they go into and how much highlighting they do. I honestly think this would be Edmentum would be a lot more helpful if they had more videos like this, which I guess I wouldn't be doing these videos if they were doing that though. So let's kind of move on. So the next thing we're going to do is algebra tiles, and our homework assignment is going to involve algebra tiles. So make sure you actually click this little link because the course or the unit activity for this unit involves algebra tiles and how to do it. So when we're adding algebra tiles, it's important to know that negatives and positives will cancel out. So I kind of glossed over that. There's two x squareds. There's three x's. There's one negative one. This one, there's two negative x's, and there's two positive ones here. So constants are kind of these one blocks. When you're doing this, you can just cross out things that are the same. So these two negatives cancel out two positives. This one negative cancels out this one positive. And then what you're left with is your answer. So algebra tiles are a neat little way of doing this. You can always bookmark it to kind of help out with that. I think it's a great tool to help you start understanding this, and they give you like an entire uh, course activity to talk about it. So when we're looking at this, we're going to combine all of our like terms, and we're going to get those two. Oh, so here's the first term right here. Actually, hold on. Oh, they're just slabbing all of it together. So negative x squared, four negative x's, and two positives. So right there. Then we also have a negative x squared and 4. They kind of just combined everything, which I don't really like. They could have organized that better. This was not a good model. Edmentum, come on. I almost feel like the people in charge of their videos are not the people in charge of how they present things. So the negative ones and the positive ones cancel, so you're left with three negative ones. And you're left with there was no x's to cancel, and these two kind of just combined. So the negatives will cancel out with positives. So just remember that when you're doing this. All right. So now we're going to be adding and subtracting polynomials. So let's get into this. All right. So we need to find which one they're equivalent to. Oh boy. So this, they kind of try to make it seem easy. Please don't just guess. Um, Distribute and do everything likely. So what I'm going to do to make this easier is I'm going to distribute like this. Oh, cool. It's a positive. That makes this easy. So I have 11x squared. Well, right off the bat, if this is 11x squared, there's only one answer. So there's no need to guess. They didn't put too much thought in giving you choices here. So the next one I'm going to do is I'm going to distribute this positive here. Well, that's a 5, and it's going to be combined with this x. So there, you could get a little confused there because that's 11x. And they're like, oh, 11x squared. Well, now you're looking at this and you're like, okay, I need an 11x. And there's two of them with 11x's. And they both have a negative 3x. So what's only thing left to do is deal with our constant. So now I have negative 12 plus 9. So that's 3. So even though this only has one quadratic, we see this one they put a little more thought on because that one quadratic has a bunch of other things. So it comes down to looking at our constant. And it's a negative 3, by the way. There's more negatives than positives. So it's a negative 3 because if I did all this thing like how they did it with the algebra tiles, um, I'm not going to do it all, but 3 of the positives, we cancel out with 3 of the negatives, but now we're dealing with it in a much larger scale. We're dealing it with 9 and 12. So it'd be 9 positives would cancel out with 9 of the negatives, and you're still left with that 3. So this one, the answer is going to have to be A. Now for our last one, let's see here. We have a negative 3x squared. Okay. That's a good argument for D, but let's double check here. I want to make sure this one doesn't have D. Well, this is 5x squared. We're going to distribute this negative, so we get 4x squared. So this one was pretty simple. Multiple choice, I never thought was the best way to learn something because you can use these little elimination strategies that I just showed you that prevents you from learning it all. Oh, I don't know where these came from. I thought I deleted everything. Okay, well, they're gone now. All right. So now we're going to talk about algebra tiles. So if we deal with these algebra tiles, oops, I see here that there's multiple ways of doing this. So you guys saw that the answer was this. I'm not going to pretend that you guys didn't see it. Sorry, clicked on the wrong one. um, but let's talk about why. Well, there's 3 negatives. There's 3 negatives. Why are there 4 negatives if I'm saying that this is the answer? Oh, actually, I clicked on it first. Oh my gosh. There are 1, 2, 3, 4, 5 positive numbers. This one can't be it because it's a negative 2 and a positive 3. That would leave you with 1 positive x. Same thing here. This is 3 positive x's because when we distribute the negative, we get a positive 3x. So you would have a positive x. This one, same thing. This is except now it's going to be negative x. This is the only one where if you distribute it, you get 3 positive 3x plus the 2x from right here. Also, when you distribute it, you get the negative 4 and the 3. So a lot of this just got determined by the x's. Like we didn't even deal with the constants. So it made it a little easier to solve this because I was so focused on the x's that once I got to the constants, it's like, well, this was the only option for x's, so it has to be the only option for constants. And you can see this to have a better explanation of it. Self-evaluation. If you don't understand the algebra tiles, go ahead and write that down. If you're having trouble distributing your negatives, go ahead and write that down. Think about it. Don't just give yourself a number and skip over to the next slide. This is an important part in the learning process, to just sit down and think what you're having trouble with. I'm not asking you to sit there for like 20 minutes. I'm just asking you, go back to the activity or think about this video that I just made and just be like, hmm, this, I still don't get this. And you can even copy and paste this into the comment section of the video. All right, so summary. All right, so the summary here, general form of a polynomial. So this is what's known as standard form. I don't know why they're calling it general form. Linear expression, so just remember power 0. Quadratic has power 2. I'm sorry, linear expression has power 1. Power 1. There's an invisible 1 there. I was thinking constant because they went linear, then quadratic. They should have had a constant there. Then there's a constant term, which has a, they say variable exponent of 0. It's an exponent of 0. I don't know why they call it a variable exponent. That's going to confuse you. And then a linear has an exponent of 1, and this one is a variable, an exponent of 2. They have me saying it now because it's right there. That's terrible. It's not a variable because we know it's right there. It can change, but then we're talking about a different function. We're not talking about that function. Anyways, sorry. I get mad at Edmentum sometimes. um, Monomial. Monomial means that one term. Binomial, two terms. I remember they're being separated by positives and negatives. Then we have trinomial, so that's 3 terms. So, for example, all of these would be example of quadratics, but in different terms. So all of these are quadratic functions. Sorry, I wasn't sure what number to put there, so I kind of froze. I was like, I don't want to keep writing 5. But this is a monomial quadratic, this is a binomial quadratic, and this is a trinomial quadratic. This makes this easier to do. Knowing the names just kind of gives you a spot in your brain to understand what type of thing it is, instead of going like, this is one of the formulas that has 2 plus signs in it with an exponent of 2. By just saying it's a trinomial quadratic, it's so much easier than wasting all that space in your head for stuff. I know it seems like, oh, I have to remember this word now, but by just being able to give it a word instead of like knowing all the different functions out there, categorizing them makes it easier. So this is just a step on how to do this. Just remember, you have to distribute those negative signs. That's really important. Group all your terms together and then combine like terms. And then algebra tiles help you model the behavior a lot better. Like I said, it is going to be part of the unit activity, so don't just gloss over this and forget about it. It's going to be part of your activity if you haven't taken a look at it yet. All right, guys, and that's it. So again, I'm sorry that it took so long for this video to come out. I know this video is pretty long, but at least you guys get a one shot to do it, and you guys can always pause and come back to it. What I usually do is I usually go to my YouTube library and just look at when I looked at the video, and it remembers where you left off. Or you can look at your history too if you're watching other videos. All right, guys. I'll try to have the next video out a lot sooner next week. Hopefully, it's not as busy. Had a lot of meetings. But other than that, you guys have a good day.